Okay, good. So I just wanted to say a word or two about all these guys. So the first homework assignment, there was more to it, but it was just this shape and size of Earth discussion. That's good. Remember I said we physicists, if we don't know this, nobody knows this, okay? Understands. So the first one was really just about the angle of a certain angle you measure on June 20th. And one thing a few people didn't incorporate was the axial tilt. Okay, so if you incorporate the axial tilt, then you have, I'll just state it here, then you have our current latitude 36.7 minus the 23.4. So we would measure a 13-degree angle between vertical and, I'll just go ahead and draw it, between vertical, which is this line here, and the sun coming in at noon, which is this one. So we will measure 13, degrees approximately. What did I say, 13.3? Something like that, 13.3. So where's the axial tilt in this picture here? Well, the fact is the Earth, the equator is actually something like this, in the North Pole, something like that. Slightly exaggerated. Okay. So that's what we had to incorporate. But anyway, so that set the stage for the second problem. And actually, I can get rid of these So we had that, and that's what we will measure if we ever get out there on June 20th. Probably the best way to do it would be to just set up a perfectly vertical stick, and then it would cast a shadow on the ground at noon, and we could use the tangent of that, right, to get an angle. Be that as it may, we then had the second problem about the sphericity of Earth. And this is the same thing we used to figure out the curvature. So I'll do this in two parts. So we had this here with radius, h, l. And h is the amount the Earth drops away as you go out horizontally a distance of L. Slightly exaggerated, we have r squared equals r plus h, the quantity squared, and then we expand that and get rid of the L. We end up with L is 2rh, L squared equals 2rh, okay? And we can work with that as well. We use that to get the orbital speed, acceleration, and so forth. Now, what we were looking for was actually the same problem in a slightly different form. So suppose we are on a mountain of height h, and we sight down to the horizon. What we're going to get is this little angle here under the horizontal, and horizontal and vertical we can get with a plumb bob. So this little angle here, by basic geometry, is the same one as that. So what we can do with our result over there is say that, and this is that L, right? This is really the exact same pictures I have over there. So we can say that L is approximately r theta. And now we have r squared theta squared approximately 2rh. Theta is 2h over r square root. So this is the angle that's measured if we actually go out to, I figured the volcano in Hawaii would give us enough elevation. That's the big one. So here the idea was to just plug in some of these numbers, 1, 2, 3, 4,000 meters, in order to see what are these angles we expect to find. Because it's always good to have some expectation before you go out and make your discovery. And what we did find was some small number of radians converted to degrees. It was roughly 1 degree for the first 1,000 meters. And Fernanda, you inverted the conversion, right? So your radians were right, but anyway, that got inverted. But yeah, so, and the rest of you guys I think had that, right? Eric, I think you had 1 degree roughly for 1,000 meters. Whatever problem that was, problem 2. Pretty sure I remember, I was just looking at those yesterday. Yeah, for down here.
Oh,
So,
okay.
but there's the radians, and then you might, oh yeah, there you go, boom, 1.01. So yeah, so that's 1 degree, and then because we go up to 4,000 meters, square root of 2, square root of 4 is 2, so we'd be measuring between 1 and 2 degrees. That means our instruments have to be, accurate enough to resolve a degree nicely. I'm sure surveying instruments do that with no problem. So if we were to go up to the coast, higher elevations, and carefully measure those things, we should get this result, and you want to do it at several different elevations to make sure you're maintaining that square root pattern. And what we would do then, or what you could do then, measuring the angles, you could conclude what is the actual radius. That would be your goal. We took the known radius just to test out roughly what our angles are going to be, but if you were doing this as an investigation, you'd carefully measure those angles, and having done that geometry, you'd be able to conclude what is the radius of Earth. So, and I'm pretty sure that's been done more than once. Okay. Good. So yeah, that was the gist of those problems. Now the second problem said, we started with projectile motion. And projectile motion, just as an example of constant acceleration. These are our limiting cases. So we really have to recognize this stuff. I always recommend if you start tutoring for the lower division physics classes, that's the best way to get practice on these things, because then you see it 100 times, right? So what we had with constant acceleration was quickly integrating up. We ended up with R0, V0, T, half acceleration, T squared. And then we discovered that that's restricted to a plane, and that's when we actually do our projectile motion, X and Y. And we can go ahead and let R0 be the origin. We know we're launching at some angle at some speed, and this is what we expect to find. And we then have X, and this is V0. So we break it up into X and Y components. We've got V0 cos theta times T, and that's it. Okay. Because we're going to have the acceleration be pointing down. Right? The acceleration G is pointing down. So we have no X acceleration, so it's just this part of the equation. This one, V0y sine theta times T minus the half G P squared. Okay. And you can work these separately now. For example, if you want the range And we're gonna call capital R the range. So if you want the range, you could take, well, the time this projectile stays in the air, you could solve here and plug in there. So I'm gonna do that. I'm gonna do this two different ways because we really want to get to know these things here. So one thing I can do, forget the V0y, that's just V0, okay, V0. So we've got V0, back up. I can factor out time from this equation. I've got V0 sine theta minus GT over 2. This is still y, I'll go ahead and write that there so we don't get distracted. And yeah, you have a function that vanishes when t is equal to 0. That's this point. And when t is equal to something else, when this expression in parentheses vanishes, that's this point. So the t we're looking for, t sub air, is going to be 2v0 sine theta divided by g. And I can now take t sub air and plug it into x, and that's how far I went in the horizontal direction. This was just measuring the vertical up and down time. So let's plug this in here. So R is equal to x evaluated at t air, and that's, we've got v0 cos theta and v0 sine theta here, so we have 2 v0 squared sine theta cos theta over g. That's the famous range formula. And if you use a trig identity for the sum of angles, I think it'll still fit on that screen there. You can end up with v0 squared over g sine of 2 theta. Who remembers that one from a previous lifetime? Maybe? Range formula? So anyway, this one's easiest to interpret because then when theta is 45 degrees, 2 theta is 90 degrees, right? So that's a 1 and that's the maximum distance. So the maximum range is at 45 degrees, v0 squared over g. Okay, so yeah, range formula, very important. And you could just keep going on analyzing this thing. Like I said, if you're tutoring 2A, 4A, they're getting all kinds of homework assignments on this thing and you can help them out. Yeah, question?
What's the fifth problem for the second homework?
Yeah, I'm not sure. Let's see what we got here. Yeah, sometimes they're being numbered differently. I only have 4 on mine. I have this one.
I ask since there's a little 5 spot and nothing here on the way you graded mine. I'm
Yeah.
just confused.
Let's consult after class. 1, 2, 3. Then we go. Speed.
I think I did 5, but I don't know if I did 1.
Oh.
An extra bit.
No, I do have a 5th one.
Oh.
Is it integrating b sub t to obtain x minus x not equal to 0 and dv dt?
Yeah, it was the
Yeah, I thought that was the first one for this week's homework.
We'll get it, no problem. Yeah. Okay, yeah, that was that integration. So yeah, I want to talk about those problems next. Let's see. So anyway, this is your constant acceleration, and these we really want to know cold because they're serving as our limiting case for everything we do that goes beyond this. So constant acceleration, good. So that's just exemplary for that. Now, near Earth orbital speed, I won't belabor. Okay, there's one problem, what I'm calling problem 3. This one we want to do. Okay, so this next problem here, it builds on the following fact. If you have a circle of radius r. Okay. And if you have your, call this the x-axis, you have a curve that just nests with that circle there, y of x. Then equals, right, and it's at the origin there. It's got its local minimum at the origin, so y of x is 1/2 1 over r x squared. And that's because we expanded the circle here in a Taylor series, and the second derivative of that Taylor series for the circle was 1 over r. So that's really important. Second derivative at a local minimum or maximum gives you the curvature of a function. Okay. So I'll say this here for small x. That's what we have. That's what we have so far. For small x. Okay. So what we then have is the problem. We're going to imagine moving through this curve and just do the kinematics of motion through that curve close to the local minimum. And what we're going to do is say we have r of t. It's going to be a vector because it has x and y component. It's going to be x of t. We said I hat plus y of t j hat. But that's going to be x of t I hat plus 1/2 1 over r x of t squared j hat, love parentheses there. Okay. So now we're just going to do the kinematics. And the kinematics is going to be velocity equals dr dt. And this one is just going to be, I'm not using the dots this time, dx dt I hat plus, we've got 1/2 1 over r, and then chain rule plays a big role here, 2 x of t dx dt j hat. So that's the velocity. What's the velocity at the origin? I'll put a little note here. V at x equals 0 is equal to dx dt I hat. And yeah, so if you're moving through this, well, you've read this. If you're moving through this, you know, down here at that minimum, your velocity is indeed pointing only in the x direction, positive x direction. It has no y component. Okay. So that is just a consistency check. Now, if we do the acceleration, which is going to be the second derivative or the derivative of velocity, we're going to have d squared x dt squared I hat. And now we have to collect everything. We've got 1/2, we've got 1 over r over 2, probably should have canceled that. Doesn't matter. And now we have to do the product rule right here. So what we'll have is dx dt for this one here times dx dt, so that one is squared, and then plus x of t d squared x dt squared. So now if we ask for, right, that looks complicated, but we want the simple version of this. So what do we have at the local minimum that we're focusing on? then x is 0 there, and the acceleration at x equals 0, a sub y, which is what we were after, is just going to be 2's cancel v squared over r. Which is a nice result. Okay. There is also an a sub x because we could be, accelerating through here or not. If you release something from rest up here and it just kind of rolls through, slides through, that acceleration might be 0. But as far as a sub y goes, here's what we have. So this is a nice example of just the technical kinematics calculation as a very standard, well-known result, okay? V squared over r, and what we've learned here is that it's just the local curvature. Probably just the local curvature. This function just was nesting with that circle there, with the 1 over r. So, two things, right? We've recognized this as the second derivative, so y double prime at a local min. That's the local curvature. Okay, so that was that problem, and there's going to be a lot of chain rule in this subject anyway. Chain rule, all these kind of calculations. So finally, anything else? Yeah. Like I said, this is mostly review today. Yeah. We'll just do this fourth problem. Get our races? Yeah. I'm going to use that simpler function, and we can talk about the other one that Thomas was asking about next time or later, but this one will do the trick. So we were doing, so here's what we had. We were doing dynamics in one dimension, and we started with a really simple function here, a bit contrived, but it has a lot of good elements there. So the first thing we do, I'm going to kind of cut to the chase. F naught over m, and when we integrate it up, 1 minus e to the minus alpha t. So that's the result of that first integration of this thing. When you write these up in future, you actually want to go back to the original problem, even though it's in your notes already, because then when what you turn in will be more of a complete thought process, okay? So you didn't necessarily want to start with this one, to start up here and repeat those. But yeah, you have this, and you integrate this one, and I'll just write down what we get. V0t plus f naught t over m alpha minus f naught over m alpha. We have another 1 over alpha, but that is 1 minus e to the minus alpha t. And one of the points of this whole exercise is that this is pretty complicated. Okay? Even though all it is a exponentially decreasing force. So the major goal of this exercise was to be able to take the limit, get the limiting case. We had done this one in class, and some of them you can do with L'Hopital's rule, or you can do with an expansion of the exponential function. Okay? You can do them either way. And this one we did in class with L'Hopital. If you do the expansion of the exponential, you can use e to the minus alpha t is 1 minus alpha t. plus a half alpha squared t squared, and so forth. For simplification of this one, for the limiting case alpha goes to 0, you can just go to here. For this one, if you want to plug in even minus alpha t, you have to use all three of these. And then what you find is, so alpha goes to 0. This one, you find v equals v naught plus f naught over m. That cancel, the alpha cancels out times t, and you recognize this as just an acceleration. Okay? So you recognize the one-dimensional constant acceleration case, and when alpha went to 0, yeah, you just had constant acceleration. So you knew you had to get that back out. This one here, when alpha goes to 0, if you include this, and you'll see the 1 minus that, it gets rid of the 1 immediately, and then you have something you have to multiply out, and you're going to end up with x equals x naught v naught t plus 1/2. Again, that f naught over m t squared. So at this point, we're satisfied that we had something right here. We may have done all the steps here, but we didn't really see it yet. So we always want to be able to take it to its limiting case. In physics, very important. And the other one is very similar. Okay. The other one we have on that other problem, I'll just note that we have expressions like 1 minus e to the minus kt over m. Okay. And in that case, we're going to have to equals 1 minus kt over m plus a half k squared t squared over m squared. And we have analogous expressions there. And in that case, when we take the limit k goes to 0, we're once again going to get the constant velocity case out there. Yeah, I have those all here, but anything to note on? Yeah, we'll get the constant acceleration case, and it all comes out really nicely. But when you do those, you gotta write it out carefully, make sure all your terms are there, so you can really see what happens, everything drops away. Good. And yeah, when you see this, right, then this is an old friend, this is constant acceleration, and all's well. So we'll get that on a couple of these problems. Good. Now, it's the last thing new that we had last time. We're already in a whole different regime, right? These culminated in the let me erase this. So these problems, we were doing separation of variables. Actually, this one we didn't do separation of variables. I'm going to go ahead and put something on the board about this other one, since we're on the subject as well. So the other problem was written out, dv dt was g, so positive direction was down, minus k over mv, right? And we did the separation of variables, so actually I should discuss this one. So we integrated dv g minus k over mv equals integral dt. This one from v0 to v, this one from 0 to t. You can prime all these. So that technique gives us v of t, which which I'm just going to write down since I have it here. So we can say something about these limits while we're on the subject. I'm gonna write both of these down. So we end up with V equals mg divided by k plus V naught minus mg divided by k e to the minus kt over m. And then we check the limits on that. I think we did that in class. Now the integration of this one is now done directly as a function of t. So we don't have to separate variables again. We just go directly here, and I'll put down what we got, x equals x naught plus mg over kt. This one's interesting, plus m over k V naught minus mg over k, 1 minus e to the minus k over m. That's a t right there, good. Point being, that looks nothing like our basic free fall, right? It's got enough going on to look very complicated, and we want to get the limiting case on this one as well. So the technique I like to do is what I just had up there on the board. We're going to expand this thing out, and if we expand this out, then we're gonna end up with 1 minus kt over m plus 1/2 k squared t squared over m squared. Okay. That gets rid of the 1, right? And it leaves us with negative of this thing here, but it leaves us with a product here, so we've got 2 times 2 things to multiply out. Remember, we're gonna get 4 expressions. And you wanna write them out really clearly, because you're systematically gonna get some cancellations. And what we're doing with this is for small k. Or you could even say for small k over m, or you could say for small t, right? For small values of this kt over m. And you're gonna find when you take the limit as k goes to 0, there will be one remnant that has k in it, so that one gets killed by virtue of k going to 0. The other one's canceled dimensionally, and you will end up with, in this case, you'll literally end up with x equals x naught v naught t plus, plus 1/2 gt squared, right? Which is the old standby. You know, at this point, we've done enough of this. I think you've learned the technique and you realize how important this limiting case business is. It's really how you check your understanding in your work as well. You know, if this doesn't come out, then you either made a really great discovery, or more likely you made a mistake. That's the idea. Good, so that was separation of variables. And in the last few minutes, we'll just kind of get back to where we are at the moment. So here's what we had so far. We had m, I'll go to the dot formulation, f of x, x dot and t. This was dynamics in 1 dimension. And that's what we've been working our way through, 1 dimension. So we had f equals mg. We had, f equals f naught e to the minus alpha t. So that was a function of time. We had f equals f of v in a couple of cases, right? What I just had on the board. And the last case that we're on now is that the force is purely a function of position. So we've gone through these, right, systematically and learned some techniques. This is the one we're on now. And what this has going for it is that you can define a potential energy, x, f of x prime dx prime. You can define a potential energy, it's just some arbitrary point there. And having potential energy, and you found that 1/2 mx dot squared plus u of x is a constant, right? So you have conservation of energy. So that's where that's what we've arrived at. And we did a couple of interesting examples with this. And actually, before I continue, and this was constant. So this was conservation of energy. Which we know from prior experience, but we've already gone a little step beyond. Yeah, before I move on, what homework problems did we have? Do we have anything for next week so far?
No.
We're a blank slate?
We only have 5 questions each day.
Right, that was fine, but we need some for next week. Which ones we're doing today?
Last one was the Earth asteroid thingy.
The what?
The last one was the Earth asteroid thingy.
It was find time t for a particle in
Okay, yeah, that was a fantastic part.
particle,
Okay.
yeah.
It was the time to collide into a center of Newtonian attraction. Which is okay, yeah, that's a very nice example. So we gotta add a few more, but, 6 minutes, we got nothing but time here to wrap things up. So we got to this, and then what we found was we could do separation of variables on this object as well. That was what we did, and that's what that problem is we just mentioned. So the separation of variables here was t equals integral dx prime 2 over m. In fact, we had a plus minus e minus u of x square root, right? Upper boundary. So that was the separation of variables, and that's that problem that we're talking about right now. The next step was, and I actually have a great idea here, was to evaluate some of these. So here I can write up another problem for next week. Otherwise, actually, if we run out of stuff to do, we can present one of these, any of these homework problems next Monday. Right, for the Monday group has plenty going on there. We got stuff from 178. So yeah, I just want to bring in another problem here. So yeah, we were finding this for different u of x. So let's take a good look at this. U of x equals, what did we call it? B times x magnitude to the m. Right, we were talking about that before, and I wanted to be a little more explicit about what this thing does between minus a and a. So this is picking up with some notes we had, but before we did that Taylor expansion, and u of a is equal to e. Okay. So now what we're talking about is u of x, u of a is equal to e. So yeah, for the quadratic one, we have this parabola. What happens as n gets larger? What happens as n gets larger, as these curves get flatter and flatter, in the limit as n goes to infinity, we can actually show that it gets arbitrarily steep. Arbitrarily steep. So, take any number, say 0.9, take 0.99 in your calculator and take that to the, say, 100th power. Right? It just gets smaller and smaller. And what this gives us here, the limit of n going to infinity on this potential gives us a square well potential, which is very interesting because a square well potential is essentially free, force-free, except for the walls. So a square well potential is the kind of thing where a ball would be bouncing back and forth. No friction and then bounce and then back again. Okay. So this is nice because this can be and square well potentials are used all over the place. Right? When you take quantum mechanics, the first thing you solve is square well potential. So this is actually a dynamical example where the limiting case gives the square well. So we had this formula, you guys can help me out on this. We had the period of oscillations in one of these potentials. I know it had a 4 there. Anybody look this one up in their notes? It was, because I had pulled out all the, I don't want to rederive it. I had pulled out all of the constants. I'll just leave some space.
Square root of 2b over n.
We can take it right there, right? 2b over m.
Integral
0
0 to a.
to a.
dx over a n.
A to the n minus x to the n. Thanks, exactly. So we had taken this one more step. Okay, we had taken this as steps where we pulled out the a as well, and then we made it dimensionless. So I'm going to put this as a homework, although we can start Monday off with this as well. The idea is to find t in the limit as n goes to infinity. And actually what we have to do is take that next step where I had made it dimensionless. But imagine you have a ball bouncing back and forth here. Okay. So it's free, so it has speed v naught, right? V, and it bounces back and forth. So we can actually say, I'll put a hint here. V naught times t is equal to 4 times a. Because 2a in the one direction, 2a in the other, and that is the time it takes to bounce back. So yeah, you'll be amazed, you gotta fiddle around with this a bit, that you can actually get the period of a ball bouncing back and forth between rigid walls off of this dynamical situation here. But yeah, perfect timing, but yeah, Monday we'll do this in a little more depth. It is a nice one. So you know all about square well potentials,
Yeah.
right? Exactly. Okay, good. That's all I've got for you.